So I'm going to look at an exam question that's come up in the past from the sample exam and see if we can pick this apart because it fits with modeling. So here the observations of the number of people who queue jumped pushed ahead of others waiting to be served at the express checkout at local supermarket was a large number. In a large number of 15-minute intervals produce the following graph. So when I'm looking at this, I'm trying to decide for myself, oh, well, I don't know what they're asking me. I've just got expected number of queue jumpers, and they're actually asking me here to pick a justification, or pick a distribution and justify it. So they're not telling me that it's Poisson or binomial or anything. I've got to kind of figure out what it is here. And so there's a few hints that are going on. One, I noticed that they've given me a 15-minute interval. So remember, Poisson often has to do with like discrete chunks of time. So on average, how many occur every 15 minutes? So since I see that per 15 minute and that hint there, that might be Poisson. Another thing to consider is that Poisson is going to be discrete data, and people, the number of people jumping the queue, is discrete. So I can see that it's discrete. I can see that it is references a time interval. And then when I look at this, I can also see that it shows sort of a skewed graph. So my guess here would be Poisson. Okay. So to talk about this, we're going to first calculate the expected number of queue jumpers in any given 15-minute interval. So this is going to relate to the expected value problems. And we can do this by hand, and we can also put it into our calculator. But what I'm going to do is just show out what I'm doing. So here first is the outcomes, basically how many jumpers you had. And this is the probability of that happening. So for 0 queue jumpers in 15 minutes, that was 0.3, just reading it off the graph, 0.3. 1 is 0.35, 2 is 0.2, and 3 is 0.15. So when I've got that written out by hand, when I'm calculating this, I'm going to times top to bottom and add them all up. So I get my expected value 0 times 0.3 plus 1 times 0.35 plus 2 times 0.2 plus 3 times 0.15. Because again, expected value is kind of looking at the probability timesing by basically how many that's going to happen and it averages out there. So my expected value here is equal to 1.2, and that's an average, right? So this is my expected value on average. 1.2 jumpers per 15 minutes. And this becomes important for us because we'll need this for solving our problem. So that expected value number is an average, and what we often need is something like the mean to use as an average. So we're going to use that in our approximation here. The store manager makes a statement to the staff that he wants the store to be known as queue jump free, defined by no more than 1 queue jumper per half an hour. So I want to watch that. This 1.2 was every 15 minutes, so I need to watch out for the fact that I'm looking for half an hour. So using what I know, the 1.2 jumpers per 15 minutes, I need to pick an appropriate distribution model. So I'm going to pause this and write this stuff so you don't have to watch me writing. So we want to remember, if we're using Poisson, there's a few assumptions that we have to make. So maybe I'll change this to say assumptions to use Poisson, because we have to make a couple of these assumptions. We don't know that it's Poisson, but we're going to use that to model it. So what are we assuming? Remember, there will be criteria for Poisson. So we have to first say that queue jumping is a random event. That's our first criteria. We can use Poisson with a random event. We have to then make an assumption that if one queue jumper sees another person jump the queue, it does not influence their decision to jump or not jump. So this means that it's independent. That's another requirement. The events occurring are independent. So we have to assume that the rate of jumpers is constant all day, every day. So that assumption of constants is a requirement for Poisson, that it's always going to be on average 1.2 every 15 minutes. And we have to assume here that only one person can jump the queue at a time. Alright? So events can only occur one at a time. So those are all assumptions that we have to state, and to get full credit for this problem you've got to be clear to clarify that you know, to state how you're using Poisson, like what's not perfect about this model, there's limitations. Are we going to assume that that on average it's 1.2 jumps every 15 minutes all the time, every day, anytime? I mean, that's probably going to have some variation between it, so we have to say that we're assuming that even though we know it might not necessarily be true. So again, to use Poisson we need to know our x and our lambda, and what we've got here is our expected value. Our average was 1.2 jumps per 15, and they're asking us here about one jumper, well, no more than one jumper per half hour. So I want to make sure that I get that to half an hour, so that means I'm going to get double this, 2.4 jumpers per 30 minutes. Right? 15 minutes is just quarter an hour. If I double that, I get half an hour at 30 minutes. So I can use 2.4, and I need to think about what he wants. So he's saying no more than one Q jumper. So that's this category that he wants to include. And our dot's always to the left. So he's okay with 1 and he's okay with 0, but he's not okay if you have any more than that happening in half an hour. So we know that our x is going to be 1, so we're going to put in p continuous because this is more than one option. It's not just 1, it's 1 or 0. And we've got 1 and 2.4. So this is going to go into our calculator and you will get 0.3084. So that's the probability that he can expect to have Q jump free, or call it Q jump free by meaning there's only at least one, or sorry, no more than one jumper in half an hour. So again, it's not a perfectly Poisson problem, but we can just go ahead and approximate and make sure that you state really clearly what your assumptions are. So remember what all the criteria are for Poisson, and that how they apply to this problem. What do you have to assume is the case for this individual problem, the context of this problem. If you're looking for another one similar to this, that video is a link to another video that was already part of this playlist anyways, but it'll take you back and remind you of that, how to solve these problems from the graph and kind of use these assumptions. So if you want another example, there's that to look at.